Welcome everyone to this Mechanics of Materials seminar series. My name is Krishna Jannalagada. I'm a faculty at IIT Bombay. So today I'll be hosting Professor K.T. Ramesh's talk on incoming the disruption of asteroids. So a short introduction about Professor Ramesh. Professor Ramesh is currently a professor, Alonzo G. Decker Jr., Professor of Science and Engineering at the Johns Hopkins University. He has a primary affiliation in mechanical engineering, but he also is affiliated with material science and earth and planetary sciences department at the Johns Hopkins University. He is currently the current director and also the founding director of Hopkins Extreme Materials Institute, which started in 2012. He mainly works in the areas of dynamic failure, dynamic mechanical behavior of materials, and mechanics of materials in general, which is very relevant to the current series, seminar series topic that is going on and organized by Professor Samit Basu of IIT Kanpur. In addition, he's obtained his PhD from Brown University in 1987, and to his credit, he has many awards. I'm only listing a few here for today's introduction. Mainly, he has gotten the Murray Medal, the Lausanne, and the Heteny Award from the Society for Experimental Mechanics. He's a fellow of the SEM, Society for Experimental Mechanics, and also ASME. And so today we will have his talk in the first, and then please put your questions in the Q&A box below. Okay, so we will do the Q&A session at the end of the talk. Okay, so once the Q&A is over, I will take up questions one after the other and allow you to speak if you are there and you want to directly ask your question to Professor Ramesh. So Professor Ramesh, the floor is yours, or the computer or screen is yours now.
Thank you, Krishna. So first of all, thank you for the invitation. It's a pleasure to be able to talk about our work. I should say it's really impressive to me that we can all get together in this kind of a format, even though I'm sitting comfortably in my home. I get a chance to talk about what I enjoy, and you folks get a chance to hear. I think we should all be proud of what our institutions have been able to do over the last few months. So getting into the meat of this talk. So I'm the one making the presentation, but the people actually involved in most of what I've talked about, you can see in the pictures on the bottom here. So let me just run through the people, starting from the right. Well, that's me. This is Andy Tonge, was a graduate student with me and is now working for the Army Research Lab. Justin Wilkerson is now at Texas A&M University. Charles Elmire is now at University Saint Louis in Paris, in Madrid. Marco Delbo is at the Nice Observatory in France. Derek Richardson at the University of Maryland College Park, and Sakshi Baru is a current graduate student at Hopkins. So these are the people engaged in the work I'm going to talk to you about. And I should say also, just looking at this webinar series, this series covers a very wide range of scales, and I might be talking about the largest of those scales in this talk. So I'm hoping to get you folks all together from where you sit in various places in the mechanics and material spectrum, and all of you come together to understand some of the issues that show up when we think about planetary science problems. So to start with, I have some pictures on the top. Let me just run through these. On the top left, this is a picture of the moon, something that you can see anytime you go out and look. Right now, the moon is in its waning part, so but maybe about a week and a half from now, if you go out and look, this is what you will see. This is a picture that's actually taken by a friend of mine in Maryland, so just a few miles from my house. Just took it with his telescope, and what you see here, you see the marks on the moon. You see these dark areas. I'm presuming you can see my pointer. The dark areas are what people call the man in the moon, or I like to see it as the rabbit in the moon. So here's the head, and there are the ears of the rabbit. But these are basically the scars of major impacts. So the moon, when every time you look up and you see the moon, you are looking at major impact events. To give you an idea of something a little more specific, let's look down here. You see this crater where my pointer is right now. I'll pull back away. You see the crater here? This crater is called Tycho. It's one of the brightest craters in the moon. And if you look carefully, you'll see these lines that come across from that crater. These are rays that come away from the crater. And these are all the signatures of the impact that caused the crater. So something hit the crater, throws out material. That material then flies out along ballistic trajectories and then falls down along lines. Those are the rays. And you can see that some of these rays go pretty much halfway around the moon. So these are very large-scale impact events. So that's the moon. When you go up and look, this is what you see. In the middle, I have a picture. Let me see if I can run it. There you go. This is a movie taken using a radar telescope of a particular asteroid. This is asteroid Bennu. Bennu is the asteroid that was visited by the OSIRIS-REx mission in the last, they had a touchdown event about 2 weeks ago. And you can see the shape of the asteroid here. This thing is about less than a kilometer across in size. On the right is another movie, which is really of, there we go. This is the elevations on the surface of the asteroid in the middle. So it's the same asteroid, Bennu. It's been visited by a probe called OSIRIS-REx. And then they've got these images, multiple frames as the asteroid rotates. So what we have up there are asteroids, reasonably large bodies, spinning. They're covered with rock. Those asteroids cause impacts on things like the moon, and you get those craters. And I'm interested in what it takes to break up an asteroid, and maybe more generally in the question of if we have an incoming asteroid coming into the Earth, what can you do about it? So that's the way in which we're going to think. The work that I'm talking about is funded primarily by NASA, and in particular through a part of NASA called the Solar System Exploration Research Virtual Institute. And you can see the icons for those two down here, or the logos, I guess. All right. So as is my wont, I'd like to start with a poem. So this is the Rubaiyat, or at least one verse from the Rubaiyat of Omar Khayyam. As some of you know, this is my favorite poem. So it's a fairly long poem. This is actually the Fitzgerald translation of the Rubaiyat. And Fitzgerald was translating it at the same time as people like Thomas Gray and so forth. So in the late 1700s, let's say. And so there's a particular style that comes across. So this is a poem now translated into English. But here's one verse. Dreaming when dawn's left hand was in the sky, I heard a voice within the tavern cry, awake, my little ones, and fill the cup before life's liquor in its cup be dry. So why am I talking about this poem? Khayyam in 1100 AD, about, is looking up at the sky, and he says, dreaming when dawn's left hand was in the sky. Dawn's left hand is what is actually called the false dawn. The false dawn is what these days in the West we call the zodiacal light. And this is a picture of the zodiacal light taken again by my buddy James Willingham from Maryland. This is what you see. So this is before the dawn. You see a bright region in the sky. The sun hasn't risen yet. The sun is still below the horizon. This bright region is not the Milky Way. The bright region that you're seeing here is sunlight reflecting off dust in the solar system. This is what Omar Khayyam saw. Now, of course, he didn't think of it in terms of dust, but that's what it is. And I want to talk about that and where it comes from. It turns out the dust is really what's left. It's the debris of asteroids and major impact events. So let's do a quick summary of the solar system. All of you have seen this in high school. So there's the sun on the left, and then not in the right distances, but just going out in order. You've got Mercury, Venus, Earth, Mars, Jupiter, Saturn with its rings, Uranus, Neptune, and then you have to decide whether we want to keep Pluto in this picture or not, which is right there. So most people these days would say, well, Pluto is no longer in the picture. The point I want to make is the solar system is like this now, but this is not how the solar system used to be. Early in the solar system, if you go back about 4 billion years, or just over 3.5 billion years, Jupiter and Saturn were closer to the sun than they are now. much closer, in fact, closer than the Earth. At some point, they began to move out. So let's talk about this, the evolution of the solar system, the way this happened. In the very early days of the Earth, so the Earth is about 4.5 billion years old. In those early days, Jupiter and Saturn were much closer in, they were much larger. And then at some point, there was a dynamical interaction that caused the two of them to move out, to move further away from the sun. So these giant planets are now moving in Earth's sky, moving away from the sun. And as they move out, they pick up other bodies and throw them in. They throw them in towards the sun. This process, by which the giant planets begin to move out, is sort of a chaotic interaction. But as they move out, they start clearing up bodies in the solar system, throwing them in, and those begin to hit other bodies like the Earth. One of those bodies, as it's coming down towards the Earth, is about the size of Mars. We call it Theia at this point. That body hit the Earth, and that major impact actually tore off a piece of the Earth, or a combined piece of the two bodies, and that's how the moon was formed. So the moon is actually the result of a major impact. Similar bodies hit similar small bodies hit other parts of the solar system. We'll look at that in a minute. But here's a simulation from Robin Canuck of how the moon forms. So you essentially have an impact, you have pieces that come off, everything is hot, and then eventually gravity brings it back together and you form the moon. All right, so this is our process. So my point is impacts have been a critical part of the solar system since its very, very early days. And this is what we want to study. Some bodies were left after Jupiter and Saturn moved out, and Neptune also moved out. And those bodies that are left are what we call the asteroids. And that's what I want to talk about. So here are the orbits of the 5,000 largest asteroids. This picture is plotted in terms of AU, which is astronomical units. Basically, one astronomical unit is the distance from the Earth to the Sun, or the Sun to the Earth. So the Earth is that blue thing here. So where am I? The Earth is this blue thing that I'm trying to track with my mouse as I go. Mercury is the red thing in the middle. Venus is the green one. Mars is that pink or magenta body. The light blue body out here, that's Jupiter. Between Mars and Jupiter, you see the main belt of asteroids. These are the largest asteroids. Some asteroids are really large, 300 kilometers, that kind of scale. Now, the moon is huge. The moon is 2,000, it's a massive body. But lots of asteroids in this domain. I want to point out a few things. This main belt between Mars and Jupiter, it's what we call the main belt asteroids, or MBAs. But in addition, if you look at Jupiter, look in the orbit of Jupiter, look just ahead of Jupiter, and just behind Jupiter in its orbit, there's a collection of asteroids that follows Jupiter and that precedes Jupiter. Those are called the Trojan asteroids. And those of you who remember the story of Troy probably understand why. But the Trojans are following along as well. So you've got all of these asteroids in the system. Now, it turns out a few asteroids are much closer to the Earth. We call these the near-Earth asteroids. So now I'm just going to plot the largest near-Earth asteroids that we know about. And what you're seeing here are those black spots of the near-Earth asteroids. Again, now you can see the Earth. It's the blue thing here. Where's my mouse? There we go. That is the Earth. These near-Earth asteroids are relatively small. They can be as small as your desk, or maybe even smaller than that. We still call it an asteroid. Typically, a near-Earth asteroid, or an NEA, has a dynamical lifetime of 10 million years. What that means is in a 10 million year period, one of these asteroids is either going to hit something like the Earth, or it's going to hit the sun, or it's going to get kicked out of the solar system because of some interaction. It looks like there are lots and lots of asteroids around the Earth, but remember, the Earth is big, the asteroids are really small. I have to make them some kind of a point in order for you to be able to see it, and that's what it looks like. All right, so my real worry here is the near-Earth asteroids, because these are the ones that potentially could hit us. So what are the asteroids made of? It turns out that if you look at them, they are actually made of different materials. So I'm showing you the same kind of picture. These are the main belt asteroids, except the color of the asteroid in this picture is determined by its reflectivity, what's called the albedo. And you can see the scale for the albedo on the right. And essentially this reflectivity is telling you something about the nature of the surface of the asteroid. So the surface of the asteroid determines what the reflectivity is. If you look at these spectra, so you can take a look at an asteroid and get its spectrum, right? The spectrum of the light reflected off the asteroid. You can say what the asteroid is made of. Most asteroids are stony. A few of them are metallic. When you look at the composition of the asteroid, this essentially tells you what the age of the asteroid is, because the longer the asteroid has been sitting there, the grayer it gets. That's because of its interactions with the sun's radiation. So the asteroidal surface interacting with protons, that's what the sun's radiation primarily is, changes the surface. You get an evolving surface chemistry. There are a few metallic asteroids. If you have a metallic asteroid, it's usually because you started with a much bigger body. It differentiated, you formed the core was metallic, the big body broke, and those metallic pieces are now floating around. We can look at the spectrum of an asteroid, we can look at the spectrum of a meteorite that we have on Earth, compare the two, and we can say this meteorite likely came from that asteroid. So we actually have a few pieces of asteroids on Earth right now. And the big question is, do all these asteroids disrupt in the same way? Because if a particular kind of body is coming in towards the Earth, if we know what it's made of, we have an idea of what it will take to disrupt the asteroid. Okay, so what do asteroids look like? Here are some pictures. This is a really nice collection of pictures put together by Emily Liptawala. So you can see some large asteroids here, like this one. This is Matilda. This is big, 66 kilometers across. You can see there's a big crater on it. Here's Ida, which is somewhat smaller, 60 kilometers this way, but much different in size the other way. So every one of these asteroids that I'm showing you has been visited by a human probe. So some kind of a satellite or a probe that we sent out that has gone by these asteroids to take this picture. Dactyl here is actually a moon of Ida, so this is a binary system. Gaspra, Eros, I'm going to show you a little bit more about Eros later. Small asteroids like Anne Frank and Steins. Itokawa, which is really small, only 500 meters across. So smaller than your campus, but on the scale of your campus, right? So think of it that way. And here are comets. The bottom four here are comets. So we visited a few of these. We know what they look like. And you'll see most of them have these craters on the surface. Okay. Now I keep getting pings. I don't know if I'm supposed to. I think, Krishna, I'm assuming you're going to tell me if I need to do something. Okay. So
yes.
Thanks, Krishna. All right. Now, just to show you that the asteroids matter, we see impact craters everywhere we look. I showed you the moon a minute ago. Massive impact craters on the moon. That's the man on the moon. We look at Mars. Mars is covered with craters. This is just one picture from Mars. By the way, any of you can go look at this on Google Mars and look at it on your phone and look at what these craters look like. In this kind of a picture, this is colored by altitude. So red is high, green is low. So if you look at this crater down here, where's my mouse? There we go. If you look at this crater on the right, you can see it has a low flow. It has a central peak. There's another crater that's hit on the side. So this Mars has been hit many, many, many times. Partly because it's close to the main belt of the asteroids, partly because its atmosphere is relatively thin. Now, we on Earth have also been hit many, many, many times, just like the moon was hit. But we have a much thicker atmosphere and we have plate tectonics, so things change on the Earth's surface. So here's the moon. This is Tycho, the big bright crater I showed you a little while ago. This is a movie made by JAXA's Kaguya mission, the Selene camera. And this is that central peak. There's a mountain in the middle of this crater. The mountain is a couple of kilometers high. You can see the dust that has slid off the surface of the mountains. Gravity. Gravity on the moon is low, but it's got gravity. You can see there's dust, so there's powder on the surface. That's not actually dust. At this resolution, those are probably a few meters across each little speck that you see there. As you move along, you can see there's substructure to the surface. So imagine a sphere of a rocky body. It got hit by another rocky body, and this is what's left. And as we move along, you begin to see lumps. You have boulders on the surface. You keep moving across to the rim of the crater. You see the rim has multiple levels. That's because the crater essentially collapses due to gravity, or the rim of the crater collapses due to gravity. Think of a sand pile. The angle of the sandpile, that's related to the gravity and what you're seeing here, right? Okay. So this is the kind of thing we can see. This is actual footage taken by a mission to the moon. And this is the Japanese space agency, JAXA. Okay, so we can see these kinds of events. We can see the signatures. We look at some other bodies, you see some interesting things. So Phoebe is a moon of Saturn. And you can see on Phoebe, it's covered with craters too, but these craters have different shapes. Look at this crater here. It's conical. We rarely see conical craters in the solar system. That suggests that Phoebe is made of a different material than everything else. And it turns out that Phoebe has a lot of ice in it. So it's not just rock, it's got some ice too. Actually, Phoebe is likely a body something like Pluto, which was originally far out in the solar system in the Kuiper belt and then was captured. The two pictures on the right, the top picture and the bottom picture, are pictures of the same spot on Mars taken a few months apart. And you can see the site of an impact. So within a 6-month window, these are two pictures taken 6 months apart, you can see an impact crater that develops. By looking at where the rays come off the crater, you can say something about the direction of the impact. All right, so there are craters everywhere, lots of impact in the system. Now we ourselves, right, are the legacy of a major impact. So you guys remember the Chicxulub crater? If you haven't, let me just walk through this. So here's the current theory that we have. And it is a statistical argument primarily due to Bill Botke and crew. But the argument is something like this. So back about 165 million years ago, there was an impact in the main belt of the asteroids. One asteroid hit another, broke it up, created a family of asteroids. An asteroid family is a collection of asteroids that all have similar orbits, very similar orbital elements, if you look at the mathematics of how you define an orbit. And the argument is the probability is that one of those impacts, one of those asteroids, one of the fragments of that impact, eventually hit the moon and caused the crater Tycho that we just looked at. And another member of the family hit the Earth and caused what we call the Chicxulub crater down in the Gulf of Mexico. And our current model, our current thinking, is that the Chicxulub crater is the one that killed off the dinosaurs. So that impact is what killed off the dinosaurs. Actually, if you look a little more carefully at the Chicxulub crater, you can see the gravity signatures. So this is a gravimetric map, and you can see the crater rim inside this. There have been much more recent missions where people have gone in, used boats to pull out cores and look at what happened under the crater. But I'm not going to talk about that. My point is, the crater is the result of an impact that killed off the dinosaurs, and it may be because the dinosaurs were killed off that we are here, right? At the time that the dinosaurs ruled the world, mammals were really, really small, and potentially we had too much competition, but now here we are, and we are the dominant species on the planet. And just so you don't think that this is only from things that happened 65 million years ago, like Chicxulub, we still get hit by asteroids. So here is a map taken from 1988 to 2020 March, which is when I took this picture, where I downloaded this. So you can see the link on the bottom left. Any of you can go to that link and you can see the current state up to yesterday or up to last week. How many impacts have occurred. The impact energy is the color. You can see it on the right in the scale. The star on the scale is Hiroshima. So that's the magnitude of Hiroshima. So we've been hit many, many times, but you guys haven't heard about it, right? That's because most of the time, what happens is these impacts occur, but they don't, the bodies don't actually reach the ground. The atmosphere breaks them up. We call these bolides that have air bursts in the atmosphere. Some of them do hit the ground, like the big red one on the right here, this one. That's the Chicxulub impactor, which did, not the Chicxulub, sorry, the Chelyabinsk impactor, which I am going to show you a picture of in a minute. But this gives you a sense of how often we get hit. So this is, NASA has required that a report be generated every few years, looking at the probability of impact. The way to look at this plot is this. The scale on the bottom is basically the size of the asteroid that's coming in. The scale on the left is the number of bodies greater than a certain size. The scale on the right is the probability of impact in a certain time. So a Chicxulub scale impactor every 100 million years or so. The scale on the top is the impact energy, assuming we're talking about something hitting the Earth. because when something hits the Earth, it's typically around 50 to 20 kilometers per second. So you give me the mass and the velocity, I can give you the energy. This pink curve is the curve of bodies discovered up to January 2016. There's an updated version of that. Everything beyond that we haven't discovered yet. So the basic argument is there are still lots of small bodies, but not very many big bodies that we haven't discovered. So there is an impact risk, but the impact risk is small. But Chelyabinsk, that happens every 100 years or so. This is what happened in the Chelyabinsk case. Chelyabinsk was an asteroid which exploded in the atmosphere above the Chelyabinsk city in Russia, in Siberia. The consequence of that explosion was a shock wave that broke all the windows in this theater, and you can see the glass fragments inside the theater. And for those of you who are interested in shocks and blasts, you should be able to tell that this is a shock and not a blast. Very good. So my point here is asteroids still couple into the Earth and create significant damage. Because the key question for us, if we think about an incoming asteroid, is how strong is it? All right, so now we can get away from planetary science and think about mechanics. All right. So let's ask, what is the strength of a meteorite? And we will assume that from there we can say something about the strength of an asteroid. An asteroid is simply a meteorite that hasn't reached the ground yet. So when an asteroid interacts with the Earth, we call it a meteoroid. The part of the meteoroid that hits the ground, we call it a meteorite. A meteoroid is also sometimes called a bolide in the sense that it explodes. If you look at asteroidal materials, the way we can look at this is take a meteorite and then measure its properties. So this is what we've done. So this is the work of Jamie Kimberley. So we got several meteorites. This is one. Its name is McAlpine Hills 8818. That means it was discovered in the McAlpine Hills of Antarctica. We get it from the Smithsonian Institution because we are funded by NASA. We then take the meteorite, we cut it up. You can see the lines along which we cut it. You can see the pieces that we've cut out here. We take any one of those pieces and we cut out samples, and then we measure the properties. We measure the properties using mechanical testing, right? So this is the typical kind of cube we get out of one of these meteorites. And you can see it holds together. It has some porosity, but it's a pretty solid piece. I should show you one other thing, actually. Let me back up. If you look here, you see the dark rim of these meteorites. There's a little rim on the outside. You can see the dark part here. That's the result of the interaction with the atmosphere. So it's coming in really fast. It heats up in the atmosphere, but it's coming in so fast, it doesn't have enough time to heat the whole thing up. You only get a rim, a skin on the outside that is heated. The rest of the meteorite is not heated up. Okay. If you go look at the cross-section, the microstructure of the meteorite, this is what you see. This is a thin section of a meteorite, then looked at in polarized light. And the colors you get because you have different minerals, and you can see it's really, really beautiful. I want to point out for you this big circle here. That circle is what's called a chondrule. It is basically a remnant of the early solar nebula. And if you look at the chemistry of this chondrule, it tells you something about the chemistry of the early solar nebula before the planets were formed. Okay, so you can take this piece of material and now measure its properties. And the way we measure the properties in this case are using a Kolsky bar. Some of you call it a split Hopkinson pressure bar, where you take a sample. So here's the pictures on the right. These are high-speed camera pictures. So every 10 microseconds, 200 nanosecond exposures. This is the stress in that sample as a function of time. So we know at frame 1, you're here, no cracks that you can see on the surface. At frame 3, still no cracks. At frame 4, now you see a crack. At frame 5, there's one crack here, but you're already beyond the peak strength. So you can look at the process of failure. And what you see is typically most of the cracks form after you've reached the peak strength. So it's not the fact that you've got lots of cracks that causes this thing to fail. It's really something else. It's the dynamics that count. So it turns out the strength of a rock is determined by the nucleation and growth of fast cracks. Dynamic fracture is what controls the strength of these geomaterials, of these geophysical materials, of these asteroids. And in fact, what determines the height at which a meteorite will explode or a meteoroid will explode in the atmosphere is determined by the speed at which the cracks can grow. If you measure the strength as a function of strain rate, you find that it climbs really quickly. So this is for that particular meteorite. So this is the low rate strength, and then you can see the strength climbs rapidly. And that's because the cracks have finite speed. So this is kind of important, right? So if you're coming in, if the incoming body is coming in at high speed, the effective strength of the body is higher than we used to think it was in terms of the interaction strength, right? The strength is determined by an interaction when it contacts something. So let's think about strength and fracture and fragmentation and how these come together. This is a really nice picture by Martin Clevis that shows you. So those of you who like high-speed photography, here's a great example. You build the doll, you drop it, and get a picture at just the right time, and you can see the concept of strength just looking at the doll itself, and then the way the cracks form. So here's the key idea. And this is sort of the one conceptual mechanics slide I want you to take away. So I have a picture on the right that looks kind of complicated. I'll walk through it slowly. So let's look at the top quadrant here. This is the probability of finding a defect in your brittle solid, your rock, as a function of the size of the defect. So when you give me a piece of material, there's some distribution of defects in it, which is this curve. All right? Keep that in your head. Now let's look at the bottom right quadrant. This is the stress needed to nucleate a crack from a defect. And basically this goes as the square root of the crack size, right? 1 over the square root. So you'll get a curve like this. So if you have a big defect, it takes a low stress to start cracks from it. If you have a small defect, it takes a high stress to start cracks. Now let's move to the quadrant on the bottom left. This is the stress as a function of time that you apply to a body. The red line is low rate loading, so the stress rises slowly. The green line is high rate loading, the stress rises fast. Now think about this. At a given time, where my cursor is, for low rate loading, at that time I will have reached this stress. That stress is enough to activate all defects bigger than this size. But at the same time, for high rate loading, I will have reached this stress. That stress is enough to activate all defects larger than this size. So if you give me a defect distribution and you identify the fact that fracture mechanics tells you that bigger defects nucleate cracks more easily, the consequence is you have rate dependent behavior. So high rate loading means more of your distribution is actually generating cracks. So you have more nucleation of cracks. Now, what determines the fact that I'm looking at a single time? It's because if you give me a body of a certain size, the fact that I have finite crack speed means it takes a certain time for my body to fail, to break, even for one crack to go across. That gives me a critical time here. So the consequence of having a defect distribution is you will have rate-dependent behavior. You don't need anything else, just a defect distribution and basic fracture mechanics. So you can then take this idea and you can build a model for scaling compressive strength. And it goes like this. It basically says, well, the stress depends on this length, and K1, of course. The effective length depends on the strain rate, because if my strain rate is high, I have more defects, right? More defects that are activated. My length also depends on the crack speed. The crack speed, then I can tie together, and my critical time that is available depends on the strain rate and whatever the strength is going to be. So I can relate the effective length to the compressive strength. That gives me this relationship, and you end up with this result. So the compressive strength of the material should go as the 2/3 power of the strain rate. That's an approximate result you'll get if the effective length goes as 1 over the strain rate. And you can modify that and extend it in various ways. You can also define a characteristic stress for a material if you know the fracture toughness, the defect density eta, and the mean size of defects S. And you can define a characteristic strain rate because you know a wave speed of some sort. And if you take that idea and say the strength must go as the 2/3 power with a characteristic stress and a characteristic rate, you find that you can fit most materials, most brittle solids into this kind of a model. So this is the normalized stress as a function of the strain rate. The line is a 2/3 power. And this includes rocks, it includes ceramics, it includes concrete, it includes things like limestone, basalt, so all kinds of rocks. So this is the basic model for strength as a function of rate, derived from the idea that defect distributions dominate rate dependence. So you can take that idea now and build a general model for dynamic behavior. And I'm not going to walk through all of this, but I'll give you the idea. So we've got a considered model that's very sophisticated. It handles contact. We're going to move clockwise along this. It handles contact. It has the equation of state. It looks at amorphization, so plastic mechanisms, including the development of amorphous bands. It has stochasticity, so the defect distributions themselves and the probability of nucleating one. Dynamic fractures, so crack speeds. The cracks interact, you get fragments, you get granular flow. You get bulking or dilation because of granular flow. You get pore compaction because you've got pores in the system, and you've got dislocation plasticity. And you can put all of this together, and you can see a model for that, for instance, in a paper like this one that's just coming out in the Journal of Geophysical Research. It's just been accepted. Okay, so we can build models and put them into integration schemes. The way you think about the model is you've got to characterize the scales here. So if you look at any given scale, you've got defects. As you crank down the scale, you get more and more defects. So as a basic idea, if you think of the log number of defects as a function of the flaw size, defect size, imagine it's a power loss or some kind of a line here. Whatever your body size is, that tells you what the largest flaw possible in the system is. The smallest flaw that's active depends on the rate of loading, as I just showed you. And the smallest flaw that you can resolve depends on the discretization in your computation. Anything less than the smallest flaw is some kind of a damage model. Anything larger than the smallest flaw, you can capture through cohesive zones or something like that. That's the basic approach. So when you change your discretization, this line will move. And that's an important thing to remember. All right, so with that, we can do basic micromechanics. Imagine you have a material with flaws in it. This is actually a ceramic with flaws. The dark regions are flaws. Each of them nucleates a crack. The crack, let's imagine it's penny-shaped. It has a normal. It has a size. You apply some loading to the crack, and let's say it's compression, so you generate wing cracks. You can break the loading up into shear and normal stresses and calculate things from there. You can then solve this as a wing crack problem. And then you can do a self-consistent method to look at what the interaction of all these wing cracks will be. So that's a basic damage model. You can do this for dynamics. Now, you can do this with tensorial damage as well. This was done by Ravi Ayagari, who I think is probably on the call at this point. But basically what this says is you take that crack distribution, right, your initial flaw distribution, and you can define a deformation gradient that includes this tensor here, which we'll call the damage tensor omega, where this VI is really telling you what the relative motion of the two surfaces of your flaw are going to be. And this Ni is the normal there. And that allows you to then compute damage strains and so forth. And you can do this for probability distributions in terms of size distributions and orientation distributions. So we've got a fairly sophisticated anisotropic damage model that you can then put into a continuum damage kind of calculation and then look at major impact events. So we've done that. I'm not going to talk about the details of that. You can go look it up in the various papers. All right. One of the critical components of this is you need a crack growth law. So L is the crack size. L dot is therefore the crack speed. You need to decide how it depends on K1 and so forth. We take this and we put this into a continuum, a computational approach, which is really the material point method, because finite elements can't do the fragmentation for us. So we take our continuum body, discretize it into a 3D grid. Imagine we've got material points inside each voxel. The background grid is basically used just for calculating the gradient. So think about it this way. I'm going to solve the constitutive equations at the material points, and I'm going to solve the balance laws on the grid. And I'll interpolate back and forth to be able to run the calculation. This process I can now do, I should go back. I can do this very fast because some people have really developed this kind of code, the material point method, into something very sophisticated that can run on lots and lots of processors. We use a code called Uinter, which is managed by the University of Utah. It's a great code, and they have been extremely helpful in letting us use it. So you can take a code like that and look at an asteroid impact flow. So here's an example. So we have the asteroid Eros, which has been visited by the Near-Earth Asteroid Rendezvous mission in 2000. Here's a movie that mission took. You can see major craters on it. We are going to simulate impact onto that crater using the code that we just talked about. And this is what you see. So the pictures on the left here, this is what the body looked like before an impact. We have an impactor coming in at 5 kilometers per second. You have the impact, you have shocks propagating through the system, you form craters, you form fractures inside the system. You can actually look at, when you look at the body, you'll see cracks on the body as well, on the real body. So you can make comparisons of this type. Okay, so with that background, what we've done so far is standard mechanics. Well, I don't know about standard, but we've done dynamic fracture, we've incorporated microstructure, we have stochasticity, we've got the equation of state built, all of those things. That's a mechanics model. But in planetary science, a big, big deal is gravity. For asteroids, gravity is really important. So let's think about this. I'm going to take my computational model, which was run on MPM, the material point method, and I'm going to add a gravitational code to it. The gravitational code is called PKD grav. And this work was done by Charles L. Mayer, whose picture you can see on the bottom right. So here's the basic approach. We have our material point method that I just talked about. We're going to interpolate that information to the grid at any given time, solve the equation of motion, reset the grid. This is what we do. That's the top line is standard material point method. Now, at some point, I'm going to decide I'm going to hand this solution off to my gravity code, which runs now in days. The material point method is thinking about the first few microseconds to seconds. The gravity code is going to look at days or months. So I take my data from MPM, interpolate to the grid, interpolate back to an equivalent particle, treat each of those as a particle, and now the particles are interacting through gravity. PKD grav is basically a KD tree. That's how it's running the calculation. So the end result is I can hand off from strength to gravity, and I can do this consistently. I can carry over position, mass, radius, velocity, damage. I will conserve momentum, but I do lose a little bit of kinetic energy. Better to lose than to gain, right? That's how it works. So now I can do gravity codes, but first I'm going to take my strength model from MPM, validate it using experimental data. So this is the data of Angela Stickle, who was a postdoc with us and is now at APL. The red points there are the MPM simulations and the rest is experimental data. So the model works in terms of strength. All right, now let's do an impact calculation onto an asteroid. So this is head-on impact onto a spherical asteroid. The asteroid is 25 kilometers in diameter. I'm impacting at 5 kilometers per second. The impact is just over a kilometer in size. Let me just run. So initially, the problem is our impact problem. All of this that you're seeing now is gravity. Gravity is bringing everything back together. And this is over time that is hours. So we have an impact. All the red is damaged material. There's a small crater on the top, and the damaged material begins to reaccumulate. The shape of the asteroid changes because I've thrown so much material away. The target is heavily fragmented, but is still together. The damaged core remains as a large remnant. The damaged core is a huge gravity sink, and so it collects material again. This is very different from what people used to think happened. So the picture in the middle here is due to Patrick Michel and Derek Richardson in 2013, where they did exactly the same calculation, exactly the same problem, but a different constitutive model because they didn't have the mechanics that we have now. And what they saw was this. The impact essentially exploded the entire target. Basically for them, down to the level of discretization, everything becomes a fragment, and all that's left afterwards is gravity. So the final shapes you see are determined entirely by gravity. Whereas what we see for the same impact event, the entire body is not damaged, is not destroyed, does not separate out, and so you end up with gravity being the primary effect and everything coming back together into one piece. Very different solutions, same problem, improved mechanics. And the key difference between the two models is granular plasticity, granular flow. So I'm going to show you the same calculation done with and without granular flow. On the left, with granular flow, and I'm showing you a cross section. You can see how much damage occurs and how much has not occurred. And on the right, without granular flow, the entire body gets damaged. Capturing granular mechanics dominates this problem. All right. We can also do this for spinning asteroids. And this is an ability that has never existed before. We can look at the spin and look at the consequences of the spin on how the body reaccumulates itself. and tells you a lot about the shapes of the asteroids you're likely to see. All right, so I've shown you I can bring these things together. Let's go back to this disruption question. The classical way of thinking about asteroids is to say, if you give me an asteroid of a certain size, I can tell you what energy it takes to break it up. And that energy is defined by this quantity called Q star. So Q star is the y-axis. This is the energy per unit mass of the target that will break up the target. And the target size on the bottom. Now, if you think about this, you can understand this, right? If the target is very small, it's a strength problem. And basically, the bigger you are, the weaker you are. And so you should start by going down like this. If the target is very big, it's a gravity problem. The bigger you are, the stronger you are. And the line should go like that. And these are a variety of different models that exist out there. And basically, I'm going to show you what Charles's result is. Basically, Charles is going to tell you that it's harder to break up an asteroid than we used to think it was. So actually, asteroids, when they get big, or reasonably big, are actually pretty hard to break. All right, so that's the theory. That's a computation. Somebody ought to do the experiment. So we are going to do the experiment. So NASA has a mission called the DART mission, the Double Asteroid Redirect mission. And this is what the mission looks like. So I'm on the mission team. We are the simulation side of the mission team. Now, it's a large mission team, I should tell you. The simulation group is fairly large. But the idea is this, that we're going to go to an asteroid called Didymos. Didymos is a binary asteroid. Here is the main asteroid, here is the moon. We can see the moon from Earth. We can see how it's spinning around the main asteroid. We will then come in with a probe, impact the moon, generate a crater on the moon, and that presumably will slow the moon down if we hit it in this direction. And we should be able to see the change in the orbit of the moon around the primary by looking at this event. So DART will launch in July 2021, and we'll see what the impact is going to look like. So this experiment will actually be done in a couple of years. So this is designed and built by Hopkins, the Applied Physics Lab. It's going to be launched in June or July, depending on some other engineering pieces. And COVID has been a problem for us with respect to that. All right. So let me try to summarize it with a few major thoughts. Impacts break up asteroids. That's the disruption problem. Gravity puts them back together. So this is the interaction. We have an impact problem that disrupts it, gravity that brings it back together. When it comes back together, it can come back as a variety or collection of pieces. The pieces we call rubble, a collection of pieces we call a rubble pile, and then there'll be dust, the really small fragments that you get from the impact event. And the interesting thing is, if we go look at asteroids, this is what we see. So this is Bennu, the asteroid Bennu that I talked about in the very first slide. Here are pictures from the asteroid Bennu taken by the OSIRIS-REx mission. And you can see the asteroid Bennu is basically a collection of rock all held together. It's a rubble pile. It may have a solid core, probably not, because the density is very low. You can look at its shape. It's like a top shape. So what's happening is gravity is causing material to slide down towards the equator. And then the equator gets fat. We see a lot of asteroids that look like that. So they're likely rubble piles. One interesting question comes up, though. Let me go back here. So think about this asteroid. This asteroid is extremely low gravity. It's very small, a couple of 100 meters across. You can jump off this asteroid and leave. So the question about this asteroid, it has small pieces of material on it, pieces of dust on it. But this thing ought to have been hit by something else, and the dust ought to have departed. But it still has dust. So where does that dust come from? And it turns out a classical way in which you can generate that is through thermal fatigue. So thermal fatigue can grow a crack in a rock. If you look at a rock on the surface of the asteroid, here's a rock on the surface of Bennu. This is actually a picture of a rock on that asteroid. You can see this big crack across it. And this is in the direction in which it's being heated. So what's happening is these cracks are growing under thermal fatigue, and that's one way in which you get dust. So you get two ways of generating dust. There's impact and there's thermal fatigue. If you look at the size of a rock as a function of the time it will survive, impact tells you this is the time it will take to break up a rock. Thermal fatigue tells you this is the time it will take to break up a rock. So you can look at this kind of a competition. So dust on asteroids might be coming from thermal fatigue. All right, so let me put this together. So you remember Longfellow's poem, right? dust thou art, to dust returnest. That's what happens to asteroids. Initially, part of the solar nebula, dust, collected together by gravity, built up into bodies, broken up by other bodies, broken up into rubble, and then throwing off dust. Then fragmenting because of the sun's heat, throwing off dust the next time they're shaken. That dust then goes out into the solar system in the plane of the ecliptic, the main plane of the solar system. The sun's light shines off that. That is dawn's left hand, the false dawn, the zodiacal light. Omar Khayyam was watching the dust when he wrote that poem, when he talked about dreaming when dawn's left hand was in the sky. And this tells you something really interesting. As the asteroids sit there, they keep generating more and more dust because of impact and thermal fragmentation. Every time they get hit, some of that dust gets thrown away. So the asteroid gets smaller. So asteroids over time will waste away. They get smaller and remove material. So let me close with these thoughts. Implications for missions. So Bennu has already been there. The TAG, the touch and go mission actually was accomplished a couple of weeks ago, a few days ago. But this is what we expect when you get to these bodies. And I should tell you, I made this slide up before Bennu, the Osiris-Rex mission was launched. Now the question is, do we see what we predicted? You should see rough, rocky surfaces because of these bodies, of the fracture processes. So you should expect to find damaged materials. We're bringing some material back from Bennu, we will see how damaged it is. So it's a really interesting question of where can you build a base safely? So right now there's something called the Lunar Surface Innovation Consortium, which is planning for lunar bases, so bases on the moon, from which we will then go to bases on asteroids and then go to Mars. Because you don't want to move mass away from the Earth. You want to go through, you want to take the mass that's out there. The question is, where can you do it safely? If what you're going to land on is a pile of dust, how do you build something that you consider? And then the other question is, what happens when your asteroid and moon base gets hit? The kinds of mechanics we're doing here will be important for that. There's a picture of the dust on the surface of Bennu. That rock on the bottom is a couple of feet across. And finally, in terms of threats and opportunities, so if you see it coming, so you have an incoming body, that's what the movies tell you is going to happen. Let's think about it this way. If the body is bigger than 10 kilometers in size, there is essentially nothing we can do. If the body is less than 1 kilometer in size, we can do certain things to it, mostly move it out of the way. Between 1 and 10 kilometers depends on what the body is made of. In general, what you want to do is move it out of the way. You do not want to break up a body. They're easy to break up in some ways. They're hard to break up because of gravity. But the end result, if you break it up, is you're going to couple all of that into the atmosphere, and that's much more dangerous. But there are also opportunities with asteroids. You could go to an asteroid. They're already broken up a little bit. You can take pieces from that and use that mass to make new materials, to make your bases. And so there are sources of material, water, habitat, fuel, all of that you can find in here. And there are a number of companies that actually do this. Right? There are companies now that are being invested in to be able to do asteroid mining. Because the key question there is, what's the surface like? All right, I'm going to stop with these acknowledgements. A number of people who've helped us on the left. Andy Tonge, of course, I showed you his picture earlier. Tim McCoy, who is at the Smithsonian and has been giving us the meteorites. Patrick Michel has given us a lot of guidance. Olivier Bonnouin of APL, Andy Rifkin there. The University of Utah, the Scientific Computing Institute for UINTA, and then the funding of these folks on the right. It's been a really valuable interaction for me. And for me, it's been really exciting to be able to take mechanics that I can do in my lab and extend that out to very large scales. And just to end with a picture here. So this is the comet 67P Churyumov-Gerasimenko. This was visited by the Rosetta mission a couple of years ago. And what they saw was this. And if you look carefully, you can see all the dust in here. That's a comet. You look more carefully, you see the dust. Let me go back. And let me point something out here. You see this rock in the bottom here? That rock, it used to be here. So it started here and then has been rolling down the hill. And you can see the imprint of the dust, of the rock on the dust. So these things are out there. We're able to visit them now. I'm really interested in seeing how these come together. Thank you very much. And if there's time, I'm happy to take questions.
Thank you, Professor Ramesh, for a very, very interesting talk, actually. So we have time for Q&A, and if you can please type in your question, I'll allow in the order they're put up there to ask the question. Professor Ramesh can respond to that. So we have one question from Sohanjit Ghosh. He asks, does everything reaccumulate or there is mass loss?
So there is always mass loss, or typically mass loss. If you have a very low velocity impact, right? So you just wave the dust and it comes right back on. But for most asteroids, the escape velocity is very low, in the order of millimeters per second. And so whenever you have an impact, you'll reaccumulate some material, but some material is gone.
Okay, so we have not many questions put up here so far. Oh, there is Shailendra. Last question. Shailendra, maybe you can ask the question yourself. Shailendra, go ahead and ask your question. I have turned on your mic. Yeah, please go ahead. I did that. Yeah, yeah.
Can you hear me, Kerry?
Yes, Shailendra, I can. Hi.
Great. Wonderful talk. Thanks, Krishna. Very, very interesting kind of combination of the gravitational aspects and the mechanics aspect that you mentioned. So if I understood the sequence of the way you presented, it seems like there may be multiple players over here in the context of how the asteroid surface ultimately forms up. One of them is certainly after, let's say there's an impact, gravity plays a role and brings back the material, but that depends on the size of the asteroid. Then you mentioned about thermal fatigue, which essentially what is going to happen is the surface is going to break down where it is stationary. It's not really a result of impact. But then you also mentioned about granular plasticity, which sounded somewhat different to me, which is potentially involve impact. But then if you compare with plasticity or with granular plasticity and without granular plasticity, essentially you can have an asteroid surface that looks very dusty, but isn't completely fragmented and still sticks to the surface of the asteroid.
Yeah, that's right. That's right. Exactly. So actually, it's a very interesting thing. If you think about asteroid surfaces, they're affected, broadly speaking, by at least four things. So let me start with the weakest thing that you might think about is solar radiation. Where you have a surface, protons are constantly hitting it, that changes the chemistry. And that changes the color of the asteroid, that changes the spectrum. You actually end up with a thin layer, 20, 30 nanometers thick of mostly iron on the surface of a basaltic asteroid. So that's one. Next level up is the impact problem. But impact is a whole spectrum of impactors. You can have one asteroid being hit by another asteroid, and that's mostly what we've been talking about, and that causes large-scale disruption. But you also have a whole bunch of micrometeorites that impact an asteroid. So you might have a rock sitting on the surface, and it's constantly being worn away by micrometeorites hitting it. And that generates small fragments that collect. So that's a second method. The third method, of course, is a large impact, and that throws pieces off. The large impact, depending on the scale of the impact, granular plasticity can be the dominant effect. So you have some domain that's damaged, but below that, granular plasticity absorbs enough energy that below that you have undamaged material. And then the fourth one is thermal fragmentation. And these things can couple. So micrometeorites can damage the surface of a rock, which creates defects. And then thermal fragmentation can accelerate the breakdown of the rock. So it's a really interesting domain. All of these things get coupled together.
Right. I mean, that was really, I mean, until now, and I have read a few of your papers, but this really came through in today's presentation that you discussed, where it seems like either it has to be a combination of mechanisms that decide what kind of surface we would end up getting, or there must be some kind of a dominant mechanism. For example, either it's going to be thermal fatigue, or it's going to be impact resulting in granular plasticity that causes the surface to be what it is. The question is, are there additional signatures from where we can decipher which one would be potentially the result or the cause of such a breakup?
Yeah, that's a really good question. And this is part of the reason why we visit the asteroids and try to bring back samples, because we have to look at these materials to see if there are signatures. Now, we have actually done that already, right? The Hayabusa mission brought back pieces of Itokawa, which is one of the small asteroids. And so we have looked at those pieces, and you see they are broken down to the levels of individual minerals. So the thermal fragmentation clearly plays a role. However, this coupling is really hard to understand. And I'm going to recommend to everybody here as they think about this, coupling in this field is very different from what we're used to in most of mechanics. In most of mechanics, we're used to the idea of sort of doing a Taylor series expansion of some sort and then throwing away higher order terms. And so when you decide what mechanisms are important, we can use that process to decide what the importance is. The problem in planetary science is you have this one other variable called time, which can be huge, right? The minimum times you're talking about are 10 million years in terms of lifetime. These things could be billions of years. And what happens is you can have terms that are very small terms, but when you integrate them over 1 billion years, they're big effects. So when you look at a surface, this thing has been exposed for 1 billion years. Solar radiation, which you might think of as being very weak, might actually do something. So this is one of the big difficulties for us, is deciding, yes, you have a mechanism, but how long is it acting? So how far back? The solar radiation, for instance, 1 billion years ago, the sun actually radiated differently. It was a different radiation amount, right? How much do you know about the history? It's a big problem.
Right.
Thank you.
Thank you, Shailendra. So we have a question from Saurabh Misal. Saurabh, I'm going to turn on your mic. You can ask the question directly. Saurabh?
Yes, am I audible, sir?
Yes.
Hi.
Yes, sir. My question is that during the numerical simulations you showed, they had smooth geometries, but the asteroids are not smooth. They have rough surfaces. So how can we account for those rough surfaces in simulations?
Yeah, it's a very good question. And you're absolutely right. We don't account for it at all in our simulations. So in most of what we do, we're looking at the subsurface damage is more of our interest than the surface damage. Now, there are some people who focus on the roughness and try to do simulations there. It's much more sort of a granular physics kind of approach, right? So you think of the surface as being a collection of boulders, and you do statistical distributions of these boulders. And what you find now is a simple, one way of thinking about it. Think of your incoming impactor. If the scale of the roughness is larger or of the order of the scale of your impactor, you are solving one kind of problem. If the scale of the impactor is much larger than the scale of the roughness, typically you find you can ignore it. When the scale of the impactor is much smaller than the scale of the roughness, you can ignore it for another reason, right? So then you're doing like a micrometeorite impact on a boulder. So these are sort of the three domains in which people work. Some people do sort of micrometeorite impacts on boulders. Some people do large impacts on large, smooth bodies. And then there's this intermediate scale where the two scales are similar, which gets really hard computationally. But there are people who do work in that domain. Actually, Derek Richardson does some, Olivier Bonneuil does some, people like John Borg at Marquette, they do some work there. It's a very interesting area also for people in geomechanics. When you're looking at things interacting with the Earth's surface. But yeah, it's absolutely a problem. You're right.
Thank you.
We have a question from Babak Rabaji. I'm turned on your mic, so kindly ask your question.
Hi, Katie. Can you hear me?
Yeah.
Yeah, very nice talk as always. So I was a little bit curious about one of the very first slides that you mentioned that showed the albedo of the asteroids that are rotating in the solar system. And something that is we can recognize in the very first glance is that we can see a trend of the albedo. When we get further from the sun, the albedo increases, I guess. Does it have something to tell us
Yeah,
why this trend happens?
sure. Yeah. So there are two effects there. So I should start by saying, in principle, we can get the spectrum of every asteroid, right? And the albedo is sort of the lowest order parameter you get out of looking at the surface. In general, for each asteroid, you actually have the intensity as a function of wavelength, if you like. What the albedo tells you really is two effects. One is the heavier bodies tend to be closer to the sun. That's usually the case, if you think about it. The rockier bodies are closer to the sun, and the lighter bodies are further away. That's usually how it is. Now, because of that, then the surface gets modified by sunlight, and so that changes the reflectivity. So albedo actually tells you a couple of different things. It tells you a little bit about what the surface is made of, but it also tells you a little bit about how long this thing has been exposed. So when you hit the body, you throw off some of the surface, you have fresh surface. That fresh surface then changes albedo as you keep exposing it. So sort of those couplings are in there. And there are people in the planetary science community who sort of make their living of looking at the spectral signature and trying to say as much as they can about the surface. There's one other component you can get, which is the thermal inertia. You can measure the thermal inertia. That tells you something about things like the thermal conductivity of the surface, maybe something about porosity. So you couple spectral signatures with thermal inertia, you can see a good bit.
Thank you. Thank you.
So Babak, I think you talked to Marco Delbo a little bit.
Yes.
Marco is an expert on that. Just ask him.
Oh, good. Yeah. Thank you. Thank you so much.
Sure.
So we have no questions yet from the participants. So I have a question. So you showed that 4-quadrant description was strength, defect distribution, the time scale. So if you have different strength distributions because of heterogeneity within the solid, so how does that plot change? I mean, I'm more interested in the constitutive response of the constituents of the asteroid or the sample that you have taken to do those experiments. So how does that plot change? Because the fragmentation depends upon the constitutive response of the different interfaces and also the individual constituents themselves. So
yeah, so that's a really good question. And the way in which I presented the model, I'm trying to provide sort of a high level view of how things work. So I completely ignored that kind of heterogeneity. In effect, all of the heterogeneity you're talking about is lumped into defect distribution. Whereas in practice, of course, there's multiple layers of heterogeneity, right? There is, if you take one of our meteorites, for instance, and look at it, and Kavan Hazeli actually did this, you can go in with a nano-indenter and measure the properties of individual phases, right? And then you can look at what the crack path is, and you can say something about the interface properties. And all of those probably matter. When you're doing a strength model for small scales, you may want to account for all of those. But as the scale goes up, when you try to do one strength model that covers, let's say millimeters to 100 meters, then you tend to homogenize some of that heterogeneity and decide that the only defects you care about are the ones where the cracks are going to grow sufficiently large that they can eventually participate in the damage of the system. And everything else you'd lump into an effective plasticity term. But yeah, it's a really good point.
Because you mentioned that in high strain rates, the number of defects that nucleate and interact is very important to define finite strength. So if you have that heterogeneity of interfaces and also individual constituents in their constitutive response, you would have some spread in that strength versus defect density sort of curve
absolutely.
that you showed at the fourth quarter.
That's exactly right. That's exactly right. Yeah, and in fact, if you look at a lot of these things, all the bodies we're looking at are sort of quasi-brittle. But But sort of a limit condition for them is you get down to the individual minerals inside the body.
Mm-hmm.
And every one of those is essentially a single crystal, relatively small. That's where your dust sits. So you break it all the way down to that scale. Then you don't break down any further.
Okay. Okay. So Shailendra has a follow-up question. So Shailendra, your mic is on. You can turn on and speak.
Thanks, Krishna. So I have a follow-up question on to Krishna's question actually.
Yeah.
So let's say you have a body that has been impacted and it breaks up and then falls back onto itself.
Mm-hmm.
Now the new body that has been formed, sort of a recycled body, will have a new defect distribution, right? And so now when it is going to get impacted, the cyclical effects are going to be quite different, I would presume, which would depend on the defect distribution. So has there been any effort on figuring out what the new defect distribution is going to be?
Yeah, and the answer is no. We really should do that. You're absolutely right. That's a critical issue. And whenever, as a mechanics guy, whenever I present this kind of work to a planetary science group, that's the very first question they ask me. So, well, we know that these things got hit many, many, many times. You're showing us what happens in one hit, right? So, what happens in the later hits? And we have not addressed that. I think it's one of those open areas. It's a difficult area. Sort of the way in which I've approached it and maybe begun to do some work there is to assume that the primary consequence of reaccumulation is that the overall body is very weak and has significant porosity. And then for the subsequent impact, porosity seems to be one of the big effects. So pore compaction is the big effect. So that's what we have tended to look at. But that's mostly because we can put in a pore compaction model very easily in our equation of state. That's why we're doing it. I think you pointed to sort of a key direction for the future, really being able to do these things for multiple impacts and developing a conceptual way of saying, this is how the effective defect distribution evolves as a consequence of history.
Right, right. And from a computational standpoint, I was curious if that would imply that, so for example, you have this coupling between the Uinta and the PKD grav, essentially telling us how the fragmented piece is going to look like. But then can you get back from PKD grav back to Uinta saying that once we have that fragmented body over a period of time, now I can tell you how that defect distribution can then be put back into something like a granular code?
Yeah. So computationally, yes, that can be done. Actually has been done. So Charles did that. But the theory that you have to use in that second impact is actually not something I'm comfortable with. Computationally, handing it back is easy, right? But then the question is, in your second cycle, what should your strength model be when you're doing the FDM? I don't have a good answer to that. I think what we are doing right now just cannot be right. There has to be something else.
That's a very interesting and probably a lot more complicated problem.
Yeah, one of the key things is you have to be able to run the calculation. So Uinta is good for that because you can scale up fairly well, but you're always going to be making some approximations to make this thing work. I think if I were doing this, and I don't have the time to do it, but I encourage somebody in the audience to do this, you could actually do this at a simplified scale. Take a body, do the experiment, reaccumulate the body, do it again. Don't reaccumulate with gravity, just put it back together in some other way. And in each case, do micro CT so you know what the defect distribution is afterwards, right? Right. Then ask what happens and then build that into a model. I think that's a great direction to go for. Nice proposal if anyone's interested.
Okay, we have another question from Agish Marcos. So Agish, I'll just turn on your mic. You can ask the question yourself. Yeah, please go ahead, Agish. Agish, you have to turn on your mic and speak. Okay, I'll probably read the question. Is there Is there a specific reason for choosing the mesh remapping techniques when other methods based on SPH formulations are available?
Yeah, it's a good question. And I think you hit on the right point. I think the question is really MPM and SPH, how different are they? And there are a number of actually particle and cell kinds of methods that you can look at that are variants of these. And let me answer it in two ways. Generally, with SPH methods, we've had difficulty being able to build the strength model in some effective way. We actually started by doing SPH. So before we went to MPM, we started with SPH. And at that time, which was like 5 years ago, couldn't figure out a way to incorporate these size-based defect distributions into the SPH codes. Maybe now people do, but at that time we couldn't do it. But I think it's a good comparison. That is the other way. And in fact, there is a group at Lawrence Livermore that has built an SPH code called Spheral, S-P-H-E-R-A-L, which is trying to do exactly that, trying to do what we do with MPM, trying to do with SPH. Eventually, the question comes down to the question of scaling. So can you run a big enough problem using your code? Essentially, I'm not a computational person. I'm using the computer science pieces that the University of Utah does, and they've really taken care of the scaling part of it. So I don't have to worry about parallelization, all of that. I do the constitutive model development, and they run the parallelization. With SPH, there are some big advantages you can have, particularly with using some of the GPU enhanced versions. So good direction to go for if you have enough of a computational mindset. I just don't have that, so I have tended not to do it. But I'd recommend you go look at Spheral. I believe it's public domain, but I'm not sure. I should have said this for everybody. The codes I'm using, Uinter is public domain. The consider models I've got is public domain. It's actually already in Uinter. You can use it. If you download the current version of Uinter, you can access those models. And we're happy to share whatever we have with everybody. I'd like to see more people using it.
Okay, thank you, Katie. So there are no open questions at this time. So I mean, the audience, if you have a question, you have to put up in the Q&A box so I can turn on your mic for you to ask, because there's no way I can hear you otherwise. I guess we have no more questions. So thank you, Professor Ramesh. Thank you very much for an excellent talk and also a great Q&A that we had today. And actually, I should also thank Sumit for giving me the opportunity to host you. It's a pleasure, maybe, and I've seen you after a long time. So I'll hand over the session to Professor Sumit Basu. If he's there, he can take over and perhaps close the session.
Yeah, hi, Professor Ramesh. It was nice hearing you. I mean, thanks a lot for accepting our invitation. It was a great talk. So we'll close it now since there are no more questions. Thanks, Krishna, for doing my job so nicely.
And let me just say, thank you very much for organizing this. I've enjoyed the series. It's really nice. I appreciate the fact that people are hanging out at what must be 9:30 your time or something. It's
yes. We have had good attendance in almost all of the talks, better than we expected. So probably this is the way to go. I mean, this is so much of trouble.
Yeah, it's some real value in it. Thank you very much.
Thank you. Thanks a lot. Thank you, Sumit. Bye-bye. Bye-bye, Katie.
Bye.
So Sumit, stop the recording and close it. Yeah, fine. You can end the meeting, I think, Sumit. Yeah.